All right, so let's go ahead and start today. Now, right up front, today's probably going to be a pretty long lecture. Hopefully it's not longer than 9 minutes, but we'll take a break somewhere in between. And what we're going to talk about today, we're going to talk about two pieces of hardware, the ALU, which stands for Arithmetic Logic Unit, and the immediate generator. And in addition, and this is why the lecture is probably going to be a little longer than usual, is we're going to start looking at how the data flows through the adder with some instructions. Okay, and also not only how the data flows through, but also what the control signals need to be in order for that data to flow through the way it needs to for a particular instruction. And knowing the data path and what the control signals are for each of the instructions is really important when we get to that control unit. Okay, I've been mentioning how the select inputs to the muxes, right? There's like 5 or 6 muxes in the adder, and all the select inputs go to the control unit decoder. And then all your read and writes that go to the different modules, they come from the control unit FSM. Okay, so, you know, after the midterm next week, remember the midterm's a week from today, like we talked about last time. Well, after that midterm, you know, there's going to be 2 lectures where we talk about the control unit. And, you know, you'll be given some time, a little extra time than what you've had for other assignments to build that control unit, both the FSM and in the decoder. Well, before you can build that control unit in System Verilog or Verilog, you need to know how the data path and the control signals are for each of the instructions. And do you remember, I think I've mentioned this maybe once or twice, but do you remember how many real instructions we have? Because, you know, it's the real instructions that actually get processed. I think the total amount of instructions we have is like 60 or something like that when you count the pseudo instructions. But does anybody remember approximately how many real instructions we have? How many? Well, there's 6. I think what you're thinking about is there's 6 real branch instructions. Okay, but remember, we have other instructions, right? Like add and.
Is it around like 25?
Close. Yeah, there you go. It's like around 30. Yeah, I mean, I don't know. I went through and I counted, and it was 30 something, like 34, or I don't know, somewhere around there, about around 30. So, you know, you really need to come up with, for those real instructions, the data path and the control signals. You know, and there's like 30 of them. Now, the good news is, and hopefully you'll start to see this by this activity that you do here in class, because unlike other lectures, this lecture does have an activity that I want you to do before you start into the assignment. Okay, and hopefully after you do that activity, and it's going to be a group activity. Okay, after you do that activity, you'll see that, you know, there's like groups of instructions that the data path and the control unit are almost exactly the same, just like a difference here, you know, 1 or 2 differences. Okay, so you know, at first it may seem overwhelming that, hey, I got to do a data and control path for 30 some odd instructions, but you'll see that it turns out to be not that many. But it's still a fair amount of work. Okay, but it's something, like I said, you have to get done before we get to the control unit. And I think it's better to do it a little by a little, like we'll do a little today, and then next class we'll do a few more, and then after the midterm there'll be a lecture we do a few more. I think that's a better approach than trying to do them all at once. Okay, so anyway, now the order of things is going to be a little different also. You know, usually I start at the left side of the board, I just work my way to the right side, right? Today we're going to start on the left, but then I'm going to go over here to the middle, spend quite a bit of time here, and then I'm going to come back to the left, and then end up way to the right. Okay, so we're gonna kind of dance around a little bit, or I'm gonna dance around a little bit up here, but anyway, you'll see the logic behind it, I think. All right, but let's start with just talking a little bit, kind of like a broad view of what the ALU is. Okay, now again, the ALU acronym for Arithmetic Logic Unit. So what do you think it does? Just from the name, right? It's going to do mathematical operations and logical operations, right? So when you have an instruction like, add or subtract or, and or, well, the operations, those mathematical and logical operations take place here, okay, in this piece of hardware. Okay. Now, when you design this, you want to design it as one mux, okay? And remember, you did a mux. Oh, you probably did muxes in CP133, and you did one in this class right here, right? Because it was part of the program counter. So when you design this mux that's part of the program counter, what statement did you use in Verilog or System Verilog? Right, case statement. So that's exactly what you want to do here. Okay? You just want to use a single case statement. In fact, there's a very good reason why we want to make this one mux that we'll get to once we start to look at the data path. Okay. So yeah, the ALU is just going to be one mux, and coming into it's going to be these different operations. You can see in the otter diagram here that we've got two inputs coming into the ALU, right? The source A and the source B. So, one of these inputs to the mux is going to be taking source A and source B and adding them together. Another one's going to be doing subtraction. Another one's going to be ORing them together. Okay, so each one of these inputs is just doing some operation, either mathematical or logical, on those two inputs, source A and source B. Okay. Now, as you can see, our select is this ALU fun. And where is this coming from again? What part of the otter is this select line coming from? Like, where's the output that's connected to this? Well, PC source is another select input that goes to the same place, the same module as this one does. Not the FSM, but the other part of it. The code, right? Control unit decoder. Yeah. Again, what connects to all the selects of the muxes is coming from the control unit decoder. What the control unit FSM provides are the reads and the writes. Okay, and eventually we'll see the reasoning behind that, but right now it's just good to know that. Okay. All right. So this ALU fun that's going to the select of the mux, that's choosing which operation. And why is it 4 bits? Yeah, because how many operations do we have here? See, this is a table, and this is on the diagram, by the way. This is a table of what the select bits for ALU fun have to be for a particular operation. Yeah, so how many do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So now, can you tell me why there's 4 bits? Right, we can't use 3 bits, right? Because how many values can we get if we only have 3 bits? 8, right? And there's more operations than 8, right? We have 11, so that's why we need 4 bits. Okay, so you see when the ALU fun select is all zeros, that's when we're going to add, right? When it's a binary 8, that's when we're going to subtract. When it's a binary 6, we're going to 4, and so on. Okay. All right, so we're going to come back to this, and I'm going to give you some more information as far as how to handle this in System Verilog or Verilog. Okay, but that's sort of just a brief overview at this point. Okay, next thing that, again, we're just going to kind of briefly talk about and come back in more detail later on, is the other piece of hardware that you're gonna design for hardware 4. Okay, hardware 4 is both the ALU and this immediate generator. Well, here, we've been dealing with immediate, right? You've heard that term before, right? Where have you heard the term immediate? Yeah, like when you do a load I, a load intermediate command, or, you know, there's other instructions in our instruction set that deal with an immediate, right? Like there's a add immediate, and immediate, and a number of others. So again, in assembly language jargon, you know, assembly language, if you have, what does immediate mean? Yeah, it's just a number. It's just some value. Okay. Now, there just happens to be 5 different types of immediates. And they're just labeled with letters here. See, there's U type immediate, I type immediate, S type immediate, E type immediate, and J type immediate. And depending on the type, the way that that value, that number is created is different. Okay. So on your table, every person should have a page. I think it's titled. But you should have this page on your table. Everybody should have a copy of this. It's right out of the assembly language manual, page 16. See, it's immediate values based on instruction format. So depending on which immediate you have, the way that number is put together is done differently. Okay? And this shows you how the bits are put together. Now, we're going to come back to this, and I'm going to go over, you know, what you need to know in order to do this in Verilog or System Verilog. Okay, in CP133, you probably talked about concatenation. Heard that term before, concatenation. Took me the longest time to pronounce it correctly, but I finally got it down. Concatenation. What's concatenation? I mean, basically, what do you do when you concatenate?
Like bringing all the slices.
Yeah, you can take like slices of bits, right? And you can connect them together in any order you wish, right? There's also replication. Okay, you can do replication. Now, maybe you didn't do that in CP133. I don't think my students did. But it's sort of like an extension of concatenation where you just like copy something over a number of times. Okay, and there's splitting of the bits, which you've done before, where you know you might have 32 bits, but you want that 4 of them, right? So you can parse out the 4 bits. Okay, but we'll review that and also talk a little bit more about the immediate types later on. Okay, but one of the nice things is that these immediates are generated in parallel. And what do we mean by that? What do we mean when we generate something in parallel? As opposed to like series, right? Because you learned in circuits series and parallel, right? Yeah, if something in series, right? Something's going to happen before something else happens. If something's in parallel, it's all happening at the same time. So when you have parallel signals or parallel outputs like we have here, you can just use assign statements. So you're going to see, you know, this mux is one single case statement. This immediate generator is 5 assign statements.
Are the 5 assigned statements for the 5 outputs?
Exactly. Yeah, you're going to have you type assigned to something, I type assigned to something, and so on, based on how the bits are put together. It's on that.
Oh, so it is, well, it was called basic.
Oh, well, that brings up another point. Both of these circuits, do you see a clock? So if we don't have a clock, what kind of just give the answer away. What kind of logic circuit is it if we don't have a clock? All right, combination, yeah. Yeah, so both the ALU and both the immediate generator do not depend on a clock. Okay, so like I said, we're gonna come back to this, both of these things, and I'll give you some more information as far as system Verilog and how to model it, okay? But the next thing we're gonna do, and this is what might take a little bit, is we're gonna start looking at how the data flows along with what the control signals have to be for various instructions. Okay, and we're gonna do 5 instructions here. We're gonna start with this subtract, then do this shift left logical, then do this add immediate, then do this one that is set less than intermediate, if I remember correctly, and then lastly this one here that's a load upper immediate. Then the activity, okay, that I'll have you do again. This will be basically the group that you're at your table. Is I'll have you at a table in a group do 2 more instructions. Okay, the scan and this or meet. Okay, and then like I said, I've got some more things to talk about also with the ALU and the media generator before you do that activity. But the next thing is, like I said, to come up with the data path and the control signals for these instructions. Now, what I'm about to write on the board is already on Canvas, okay? Because on Canvas, where I have basically an outline of my notes, I put what I'm going to do on the board, okay? So, you know, I know some people like to always copy down in their notes whatever's going on because it helps them retain things, and that's fine. But I just point this out because if you don't get everything, I wouldn't worry about it because you can just go to Canvas and put whatever you missed. Okay? All right, so it's good to use 2 colors. We're going to use red for the data path, and we're going to use blue for the control signals. Okay, so we're going to start with, oh, and also while we go through this, it would be, I think, advantageous, you know, beneficial to you if you're looking at the instructions. Like I have my instruction manual here, a hard copy of it, but it's on Canvas, right? So you could look at it on your computer as we're going along. Okay. All right, so we're going to start with this instruction here, the sub instruction. Okay, so what does this instruction do? It's going to subtract now. When we have, or when you look at an instruction, you see X5, X10, X20. I mean, what does that tell you right away? Because where are X5, X10, and X20? What piece of hardware? Yeah, they're in the reg file, right? Right. Remember when you designed the reg file, you were looking at that handout that had the 32 registers, right? Okay, so in this instruction, which register is our source 1 register, which one's source 2, and which one's our destination register? Yeah, X5 is our destination register. Which one's source 1? Which one? Is it X10? You looking at the instructions? Everybody agree? And this one's source 2, right? Yeah. All right, so what does this instruction do? It subtracts, but what does it subtract?
Source 1 minus source.
Yeah, I'm pretty sure it's source 1 minus source 2, right? So let's make sure. Let's look at a manual. Let's see, what does it say? Sub instruction subtracts the value in source register RS2 from the value in R1. So we did write this right? It subtracts value in source 2 from the value in source 1. And then where does it put the result? Right, yeah, the result always goes to the destination register. Okay, and in this instruction here, it's X5. Okay, so this equals RD. Everybody good? All right, so now let's go over to our diagram, and where we're going to start the data path is here at the output of our program counter. What do we have at the output of our program counter? Because what does the program counter provide? The address of the instruction that's going to be executed, right? So you see? Here's the address of the instruction. Okay, this is just my abbreviation for instruction. Defense. And that's gonna go to, right, the output of the program counter is connected to this address 1 input of our memory module. And why would we want to connect the address of where our instruction is that's going to be executed? Why would we want to connect it to this module, this memory module? Because what's in that memory module? Instruction, right? Because remember, the memory module has a segment called the code segment. Right, and that's where the instructions are. Okay? Now, notice, coming out of the program counter, we've got 32 bits. But this address 1 input, right, of our memory module, it's 14 bits. Why is that? What's that? Well, the address of the 3 registers are over here, because remember the, the source 1, source 2, and our destination register, they're over here in the reg file. Well, how many values can you represent with 14 bits? If I have 2 bits, how many values can I represent? 4, 3 bits, 8, 4 bits, 16, 5 bits, 32, right? Every time you add a bit, you multiply the values you can represent with those bits by 2, right? So you see, when you get up to, more than like 10 bits, you know how I think quickly of how many values I can represent? Because I know 2 to the 10, right? How many values I can represent with 10 bits? I know that's 1K, right? Which again is 1024 in the digital world. And I know that every time I add a bit, I double the number of values. So you see, I just remembered 10 bits, 1K. So then if it's 11 bits, it's 2K. If it's 12 bits, it's 4K. If it's 13 bits, it's 8K. If it's 14 bits, 16K. All right, so if you have 14 bits, you can represent 16K, 16 times 1024, whatever that number is, values. Now, where did this come up before? Because we talked about something in the memory module that was 16K.
Isn't that the length of the code?
What's that?
Is that the length of the code?
Right.
Segment?
Oh,
That's how many instructions we can fit in our code segment. Because remember, the code segment goes from address 0 up to 0005 FF, I think it is. Right, which is 64K. But then that's bytes. And there's 4 bytes in a word, and instruction's a word because an instruction's 32 bits. Well, 64K divided by 4, that's 16K. Right? So you see, that's why there's 14 bits here, because at most we have 16K instructions. Right? Does that make sense? Now, let me ask you this. Look. The 14 bits that we're using go from bit 2 to bit 15. It doesn't start at bit 0. See, bit 0 and 1 is not part of this. Can you think of a reason why? Well, instructions start at 0, right? Remember that we talked about how, at the very beginning, right, you're going to reset the adder. And when you reset the adder, the output of the program counter becomes 0, and that's where your first instruction is. But where's the second instruction? 4. Where's the third instruction? Where's the next one? Right, they're going every 4. Do you need the last 2 bits if a number is divisible by 4 or not? Divisible by 4, because you did that in a homework assignment or one of the assignments. Remember that if you wanted to see if something was divisible by 4, the last 2 bits are 0. So remember, this memory module was designed by Dr. Hummel. And I haven't looked at it closely, but you can bet that he set the last 2 bits inside to 0, right? Because you don't care what those 2 bits are, since the instructions are every 4 away an address. Okay, so that's why this is 14 bits, and that's why it's 2 to 15. Okay? All right, so now we have the address here of our instruction to be executed at this input of memory, and we want this read enable, okay, which is a control signal that's coming from the FSU of the control unit. We want that to be a 1, right? Because when this gets clocked, we want the instruction at this address to be at this output, right? So at DL1 of this memory module, when this read enable 1 is 1, right? Once it gets clocked, well, now it's going to take that instruction at this address and put it at this output. Okay, so here we're going to have the instruction, right? The instruction to be executed. Okay, now that comes over. And these 5 bits go to address 1 of the reg file. These 5 bits go to address 2 of the reg file. These 5 bits of the instruction go to the right address. Also, bits 31 through 7 come down to this immediate generator. Okay, but for this instruction, does it have an immediate? No. So for this instruction, whatever these bits are going to the immediate generator, we don't care. They're not going to be used, right? We don't have an immediate, I mean, there's going to be bits there, but we don't care. They're not going to go anywhere, okay? But we do care about the bits here, right? Because that's part of the instruction. So what data are we going to have here on address 1 for this instruction? Yeah, it's going to be 10, right? Because we want the contents of register 10 that's in the reg file. So this is just going to be a 10. What's going to be the data on the address 2 input? 20. What's going to be the number, the data on the right address? 5. Hey, remember, let's see, what class was it? Was it last class or the class before? But there was a recent class where we showed the machine code for an instruction just like this that had RS1 and RS2 and RD in it. And sure enough, the binary, right, there was 5 bits, right? These 5 bits, and sure enough, there was the binary for that particular address, right? Okay. So now what kind of outputs are these? When you design this reg file, what did you make the RS1 and RS2, the reads? Async, right? So as soon as the data is there for address 1 and address 2, now the contents of those registers at those addresses are going to be here. Okay, so now at RS1, you're going to have the contents of whatever register 10 has. So I'm going to represent that with an X10. Okay, so whatever data is in that register, whatever 32-bit data is in that register 10, now the contents is going to be our RS1. And the contents of register 20 are going to be at this output. Okay? All right, so now continuing on here, and I've got to draw the red lines, but there's red lines here. Okay, so continuing on, this data here, the contents of register 10, it goes to this mux. The contents of register 20 goes to this mux. And we want to do subtraction, and that happens in the ALU. So what do I want this ALU source A to equal, which is the select of this mux here? I want it to equal 0 because I want that data in register 10 to be at the input of the ALU, so I can do subtraction with it. So you see, this is going to be, let's use blue for the control. So this is going to be a 0, right? And that's going to take this data and connect it to the output of the MUX, which is going to be input of the ALU. What do I want this select ALU source B to equal? I want it to also be 0, right? Because that will connect the contents of register 20 to the input of this ALU, 0. Now I want to do subtraction. So what does ALU fun have to be? What does this select have to be if I want to do subtraction? You're going to look over here, right? It's just going to be 1 0 0 0, right? 8 in binary. So see, this would be 1 0 0. And again, this is coming from the control unit decoder. This is coming from the control unit decoder. This is coming from the control unit decoder, right? All these selects are coming from the control unit decoder. This memory read, that's coming from the control unit FSM. Okay, so now what else do we want to do? Well, now we're in the ALU, right? We got the content of the 2 registers in the ALU, so we're going to do subtraction in the ALU. Then we're going to have our result at the output of the ALU. And what do we want to do with that result? Right, put it in register 5. So that's why you see a connection like this on your diagram that goes up to this MUX, whose output is the write data of the reg file. So what do we want this select line to be in order to get that data to this write data input? Coming in right here. You want it to equal 3. So you see this will be a 3. Again, this is coming from the control unit decoder. So now the result of our subtraction is going to be right here. And we want to store that in register 5. So in order to store it, what does this reg write have to be? It's got to be a 1. Right, and the clock on a clock pulse, because it's synchronous, that's when the write will happen, and it puts the result in the register we specified, which is register 5. Okay, now we're not quite done. To finish this, we also have to come back over here, because now, you know, that instruction has been executed, right? We got the result in register 5. So we take the address of that instruction, right, that has been executed, and we increment it by 4 because why? That's where the next instruction is, right? It's 4 away in address. That comes over this MUX. And as long as we're not branching or jumping now, next class on Thursday this week, you know, we're going to talk about the hardware and instructions, you know, what happens with the various branch instructions, data and control signal wise for the branch address generator and also the branch condition generator. So, you know, this is on Thursday. You know, Thursday up here. Okay. So we're not branching or jumping or anything like that. We're just going to the next instruction. So if we want to go to the next instruction, what does PC source have to be? 0. Right, that's going to connect, you know, this address that's been incremented by 4 from the previous address to the output of the MUX, which is going to go into the PC counter. And now to advance to that next address, right, that's 4 away from the one we just executed, what does PC write have to be? 1. Right, now the next instruction is going to be here, and we would just go through it again for that, whatever that instruction is. Right, and let's say the next instruction was this one, right? We just went through this one. Okay, and let's do the same thing. Let's follow the data path and do the control signals for this shift left logical. Now, before we start this one, because, you know, before I start this one, I have to erase everything in red and blue. Do you have any questions about what we did with this instruction?
When you say next instruction, you're talking about the instruction that's the address for bits away.
Say that again.
You're talking about the instruction that the address 4 bits away from the previous one, and you're saying next.
4 addresses away.
4 addresses?
Yeah, because remember, each address is a 32-bit address.
Okay, but if you have a series of instructions, right? Next to each other, address wise?
Well-
Skip address it or?
Well, you would never have instructions that weren't 4-way an address. The reason being that all instructions are 32 bits. And remember, our memory is byte addressable.
Sure, but they're not all four, they're all divisible by 4, but each individual address is got 4 away from each other individually, right? I mean, one address is 4
Okay.
away, another one is
You-
8 away, another one is 12 away.
Well, your question gets to how memory is organized, how we talked about, just real quick. Remember how we talked about that? You know, you can look at memory where, you know, each row is 32 bits. And since memory is byte addressable, each byte has an address. So, you know, this byte starts at address all zeros, then this is all zeros, 01, right? 02, 03, and then this one would be 004, and so on, right? These are separated by 4. So because instructions are 32 bits, and because each byte has an address, each instruction has to be 4 an address away. Like this instruction at address 0, then this instruction at address 4, this instruction at address 8, and so on. So it's because how memory is organized that it results in each instruction being separated by 4 an address. You'll never have like an instruction at address 2, right? Because, you know, the hardware doesn't allow you to cross what's called word boundaries. Like if you tried to use address 2 or word address, it wouldn't work because if this was a word address, it would try to take this byte, this byte, this byte, and this byte. And it won't cross what we call word boundaries. Like the hardware won't allow that to happen. Now, unless you're doing a branch or a jump, the way the program is going to be executed is every instruction that's 4 away, right? Because PC force, if you're not branching or jumping, PC force is going to be 0. Again, the control unit decoder is going to be designed like that, where we're always going to choose the next instruction, which is 4 an address away from the previous.
How do we know that instruction, what we want to do? Right? So how do we know that? So if we're doing subtraction, then you're doing shift left logic.
Oh.
How do we know that those are in a row? Right? Like what?
Well, when you make the mem file, like when you're in RARs, right, and you put in your program and you make sure it's okay, and then you generate the mem file, that's what the assembler does. The assembler takes your assembly language and turns it into the machine code, and it puts it at the addresses. So it's going to put the first one at address 0 and the next one at address 4 and so on.
Right.
Yeah, but the other thing that your question brings up that I want to make clear, I don't mean this to be a program. I just randomly took some instructions just to show this. So this isn't necessarily a program. It's just, you know, each instruction I'm treating individually just to show you the data path and the control. Okay, is that
Yeah, that last bit answered my question.
okay? All right. Well, eventually we'll get there. Okay. Good. All right. So, any other questions before I erase this? We're starting the next. Okay, so let's erase this. If I miss anything, let me know. Try to get it all here. Alrighty, we're getting there. You see any that I missed? Did I get them all? Oh, I know it's gonna miss some. Any others? Okay, so you ready for the next one? All right, so what kind of instruction is this? What does SLL stand for? Yeah, I think it's a logical shift, right? Logical shift left. Let's get to where it is. Yeah, so it's a logical shift left. So what is RD? What's the destination register? If this is RD. And what else we have here? What's this? Source one. This must be source two, right? All right, so what is this instruction going to do? Yeah, I think what it does, if I remember right, it's going to take whatever's in register 12 and shift it left by whatever numbers here and put the result here. Okay. So I won't write it down because it's right in your instruction manual, but that's what it's doing. Okay. All right, so let's follow what the data path is, and also what the control units have to be, or control signals, I mean. Let's see, where's my notes? Let's subtract. Oh. Okay, so we're going to start where the addressing instruction is. All right, so again, here's the address instruction to be executed. Our memory read enable one has to be, or yeah, memory read enable one. What does this value have to be? A 1, right? Because in order to read, to get the instruction at this address, we need this to be a 1, right? Along the clock code. So this has to be a 1. Okay, now the instruction is at the output of the memory module, right? These 5 bits go to address 1. These 5 bits go to address 2. These 5 bits go to the right address. So what number are we going to have here on address 1? Well, remember, when you put an X, like X12, that's really talking about the contents of the register. So it's just going to be the address, which would be 12, right? So we're going to have 12 here. What are we going to have on address 2? 15, right? And then what are we going to have for right address? Okay, so now the contents of register 12 would be at this output here. Okay? So the contents of 12 would be there. Contents of 15 would be there. Oh, actually, I should do it. Sorry, using the wrong color. Remember, data is red. You only want to make your read and write in select lines blue. Those are the control signals. So this would be, what was it again? This would be the contents of 12. This would be the contents of 15. Okay, so this data goes to this much. This data goes to that much. So we want to take that data and again, input it to ALU. So that's where the shift left occurs, is in the ALU. Okay, so what do AL source A and AL source B have to be? 0. They both have to be 0. All right, so now this data is at this input of the ALU, this data is at the other input of the ALU. So now the shift left happens. Now, the symbol that we'll use a lot of the times in these diagrams for shift left is, showing an arrow to the left and then a little S. That's to distinguish it from like, right, like a less than or something. Okay, so the shift left happens, and now the result is here at the output of the ALU. Oh, I forgot this though. What does ALU fun have to be in order for a shift left? Logic. Come over here. shift left logic is a binary 1. Right, so this would have to be a binary 1. Okay, now we have the result of the shift at the output of the ALU. That comes up here. So what do we want this select line to be of this mux? 3. We want that data to be at the output of the mux. And then we want to write it to the destination register. So what does this have to be? That has to be a 1. Okay, so that data now is in register, what is it? Register 6, right? The destination register. But then also what's got to happen is we got to increment that address. Right? The instruction address got to increment it by 4 because again, that's where the next instruction is. And then PC source has to be what? 0. And that's going to put that next address at the input of the program counter, and then to get it to actually go to that address at the output, we need PC write to be 1. Okay. Now, remember I said at the start of the class that the ALU, you want to make it 1 month, right? Which is 1 case statement. And you see, in this particular case, that's very important. Like, you would not want to try to do the mux with like a bunch of if statements. What Verilog and System Verilog tend to do, if you use like a long if statement, is it tends to make the hardware in chains. You know, more like a series type of circuit as opposed to just one module that the signals have to travel to. And you see here, it's particularly important because remember we talked about, or I briefly mentioned last class, that most instructions take 2 cycles to be processed, 2 clock cycles. Okay, we're going to go into more detail, after the midterm and look at timing diagrams and looking at the timing aspect of this in more detail. But what I want to mention right now is that for most instructions, 1 clock cycle is getting the instruction to be here. In fact, it's called a fetch cycle. We're going to call it a fetch. So basically, it takes 1 clock cycle to get the instruction at this point. Then you need all of this to happen. You need everything that happens from when the instruction is available at this output to when the result is finally written to a register in the reg file. You need that to happen in 1 clock cycle. It can't be longer than that. And if you have an ALU that's like a chain of circuitry, it's not going to happen. The timing's not going to work. Okay, so that's why the ALU has to be simple. That's why it's just 1 case statement, 1 big mux, because then it just has 1 piece of hardware to go. Okay, and that helps with the timing. Okay. All right, why don't we take, because we got 3 more instructions to go through, plus I got to say a little bit more about, how to do this stuff in Verilog, and then you got the activity. Let's take like a 5-minute break, and when we come back, we'll pick up with the 3rd instruction. Okay?